Whoa, was that a turkey? No, that was just me clearing my throat. Hey there, it's Mr. Pouts with section 12.4. And this one is about angle measures and segment lengths dealing inside of a circle. So we have two goals. The first one is to find measures of angles formed by chords, secants, and tangents. So we've learned about tangents and chords. We'll learn about secants today. And also then our other objective is to find the lengths of segments associated with circles. All right, so we'll have a number of theorems again in this section. But to get us started off, angles formed by chords, secants, and tangents have a special relationship to the related arcs formed when the lines intersect. So first term is a secant. What is a secant? That's a new one for us. A secant is a line that intersects the circle at 2 points. So a tangent just intersected it at 1 point. A secant intersects it at 2 points. And it actually goes straight through. And a chord, so good review, a chord is part of a secant. So we have our chord right here. All right, going on. Let's start off with a couple of theorems. And these two theorems, we're just going to take them for what they are. I could certainly prove them for you, and we could walk through the proof. But for time's sake, we're just going to accept them because they've already been proven. So theorem 12.13 says the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So, for instance, measure of angle 1. That would be half of whatever x plus y is, those arcs. If we do another one, like right here, angle, and then obviously the opposite side is the same. But let's say this is angle 2. That would be half of whatever this one is and this one added together. Okay? So that's when they intersect inside of a circle. That part is important. If they two lines that intersect inside a circle. Because theorem 12.14 deals with two lines that intersect outside of a circle, whether it's two tangents, two secants, or one of each. It says the measure of an angle formed by two lines that intersect outside of a circle is half the difference of the measures of the intercepted arc. So we're just going to take whatever the biggest one is, bigger one minus the smaller one. So we'll do x minus y. All right, so it's half the difference between those. All right, very interesting that that was proven. So let's use those. We're going to skip over this proof right now. You can certainly look in the textbook if you'd like to see how that works, or look it up. We're just gonna do some examples with that right now. So I think yours are broken up a little bit different than mine, but they're mostly all the same problems here. So let's just look at number 1 and number 2 for right now. They're basic problems for using these. So it says, the first one, find the value of each variable. So we're trying to find the measure of this angle, this x. So this one is outside of the circle. So if we look at that, that would apply theorem 12.14. So it's 1/2 the larger angle minus the, or larger arc minus the smaller arc. So 1/2 of 72 minus 22. 72 minus 22 is 50. So it's 1/2 of 50, which we get is 25. So that makes that a 25-degree angle. All right. Number 2 is different because it intersects inside the arc, but we're not looking for the angle. This time we're looking for one of the arc measures. We're also not given the angle. We're given an angle that would form a linear pair with it. So if this is 139 here, that means that this would be whatever 180 minus that would be. Minus, come on, stay there. 139, which would be equal to 41. All right? So that means that the angle 41, if it's inside, it's equal to 1/2 the sum of the other two. So x plus 40. Now we just have to do some algebra, prove that we know algebra, and solve for x. So go ahead and do that for me. All right, there's a couple different ways you can do it. I'll just distribute for the sake of distributing here. 1/2 x plus 1/2 times 40 is 20. Wow, that just went crazy on me. Let's go back down to here. Using our Superman colors, blue and red. 20. We'll subtract 20 from both sides. So 1/2 x equals 20. Oh, wait, this is 41. So 21. And then I can multiply both sides by 2 to cancel out that 1/2. Multiply by 2 over 1. So x. So multiply by 2 over here. X equals 2 times 21, which is 42. All right. So we're essentially finding the average of those two to find that angle. All right, we've got a couple examples here where it's a little bit more in depth, a little more going on with this. Let's choose at least one of these to work through. How about why don't we just look at number 3? Okay, so we're trying to find both x and y, and I want to think about how we could go about doing that. So let's look at, what do you want to look at first, x or y? Sounds good. Let's do x. All right, so x goes, actually this would be one of the arcs. This would be the other arc. I think this one goes through a diameter, so this would be 180 degrees. This one would be, well, we got 70 and 30, which make 100. That leaves this one would be 80 degrees. Okay? So if it's inside of the circle, x is equal to 1/2 180 plus 80, which would be 1/2 of 260, which is 130 degrees. So x is 130 degrees. Now with y we're just dealing with, I guess we have two lines that intersect outside of a circle. So if we're looking at that, we're looking at this angle right here. So one of the arcs is right here, which we're trying to figure out that y. We're also dealing with this other arc, which goes from right here to right here. Maybe I should use a different color for that. This one goes from here to here. Oops. Black. From here to here. This one goes from there to there. Okay? So this one right here, this black one right here, would be a total of 180. Because that is a half of a circle. That's a semicircle. We're trying to find this one. So let's use the theorem where it's outside of the circle, which is the second one. The angle measure is equal to 1/2 of x minus y. So 36 would be equal to 1/2 of 180 minus that y. And here we go. Here's some algebra for us again. I'm going to do this one a different way. I'm going to multiply both sides by 2 first, cancel that out, and multiply by 2. So I have 72, 70, I keep getting my 2's and 7's mixed up. 72 equals 180 minus y. I think I'm going to add y to both sides and then subtract 72. So I'm going to add y. So I add y over here. I'll move this over here. Then I have y plus 72 equals 180. And I subtract 72 from both sides. We get a total of 108 for y. So y is a 108 degrees, it looks like. All right, and that's just applying, I applied both of them. With all the lines in there, the chords, the secants, the tangents, it kind of seems like a lot, but that is applying the second, or both of them at the same time. You can go ahead and try numbers 5 and 4. For right now, though, I'm going to move on to the second part of this, because this is a longer lesson, where we're dealing with Theorem 1215 to start off. It says, for a given point and circle, the product, Okay, so for a given point and circle, the product of the lengths of two segments from the point to the circle is constant along any line through the point and circle. So we have a point here, whether it's inside or outside. But there's a special formula, I guess you could say, but really it's a constant, we'll just go with formula for right now. That would work for every single time given the different situations. So the first situation is where you're given two chords, or it could be considered two secants, but it's intersecting in the inside. So the relationship that we have is that A times B, so the two parts of the red one, um, equals C times D. And that'll work for every single time, every single one where there's two chords intersecting inside of a circle. I don't know how somebody came up with that, and actually I do, because we can prove it right here. We're not going to do that. But crazy that someone would even think about that. I think it's pretty cool. The second one, if you're dealing with what would be two secant lines, because they both intersect at two parts of the circle, but they intersect outside of the circle, would be that W plus X, two parts of that blue line, times the outside part, the W, would be equal to the red one, Y plus Z times Y, which is the outside one. Again, crazy relationship, but it'll work like that every time. And trust me, these are probably three of the hardest cases to remember, or formulas to remember. Um, but looking at case 3 then, we have one that would be like a tangent line because it only intersects at one part, and then one secant. And this one would be the y plus z, the red one, times the y again, is just equal to t times itself, or t squared. So, let's try to use those things. Skipping over the proof right now. Let's go through a couple examples so we can get these practiced. Examples, find the value of each variable given or using the given chords, secant, and tangent lengths. So this looks just like the first case. The first case said that A times B, so like we can use A and B would be 6 and 5. 6 times 5 is equal to X times 10, or 10 times X. So 30 equals 10X, divided by 10, you get X equals 3. Just from that one relationship that's been proven. And it kind of does look like it would be about 3. That's a pretty accurate one there. Number 2, this one comes from case number, well, if there's, looks like two secant lines, would be case 2. And that's where, okay, so we have, let's just work it out. So it's the 12 plus the 3, which is the whole length of that one, times the outside one, which is 3, is going to be equal to the x plus 10 times the outside one, which is x. So this might be get a little tricky too, dealing with what we have there. We'll see. So let's solve it. This is just 15, and 15 times 3 would get you 45. So 45 is equal to, distribute, x squared plus 10x. Uh-oh. We have a quadratic, so I'm going to subtract 45 from both sides. So now 0 equals that. And now we can use a quadratic formula. We can do the factoring method, if that works, which it might. Let's see, what two numbers multiply to equal negative 45 and add to equal 10? 9 and 5, 15 and 3. Unfortunately, I don't think there's a whole number in an integer that would work. So this is going to get sloppy. You can use the quadratic formula. There are other methods, but you'll end up getting about negative 13.4 or 3.4. And obviously, you can't have a negative distance So it is about 3.4. All right, too bad that doesn't work out nicely. But it does look like it's a little bit over 3. So that's what we get for number 2. And let's move on to number 3. Let's do number 3. All right, number 3. We have a lot going on here. So let's look at the small one. The smaller one looks like this line right here. No matter which side, which one is going to be on, it's a tangent line. So let's just look at the smaller one to find out x. So if we look at that third one, it's the distance of if you add up the two parts of the secant line, multiplied by the outside part, it'll be equal to the x squared in this case. So 18 plus 8 times the outside part with it, which is 8, would equal x squared. Okay, 18 plus 8 is 26. 26 times 8, I'm going to use my calculator, and I get 208. And if I'm going to find the square root of 208, you end up getting, well, x would be equal to the square root of 208. It's about 14.4 something. Okay, not pretty again. So, well, I hope we did that one right. Looking up there again. Y plus z times y equals t squared. 18 plus 8. Oh, I did it wrong. Times 18. Why did I do that? This is times 18. 18 is the outside one. So, also alarm 26 times 18. And you take the square root of that. That's not any better. You still get the square root of 4. So 26 times 18 is 468. Square root of 468. We're going to leave it at that for right now because it's about 21.6, and you could reduce the radical. We're going to leave it like that for right now because we can do that with the other one now. We're still dealing with that secant, so x squared, which we have is the square root of 468, would mean that you'd have square root of 468 squared, which that would cancel out the square root, is equal to y plus 10 times the outside one, which is 10. All right, so this would be 468 equals 10y plus 100. Subtract 100 from both sides. 100. 10y is equal to 368. And you divide 368 by 10, you get a whopping, whoops, 36.8 for the y value. And again, looking at it, that actually looks pretty accurate. Okay, so that's the last one we're going to do with that. There's lots of more practice with this section that you can utilize. We have a few here and going on from there. But for the sake of time, we're going to end it. This is already a long enough video. So take a look at the goal and see what you learn. A lot of stuff goes into this. 2 goals, finding measures of angles formed by chords, secants, and tangents, and also finding the lengths of segments formed by those lines. All right? We'll see you next time.